In our last few lectures, we have talked about ordinary differential equation solver, in particular initial value problem solver using numerical methods. We have learned Euler method. We have also learned a family of methods that we call Runge-Kutta method. In particular, the fourth order Runge-Kutta method will be most important for us. This method is highly accurate and it is useful in general for ODE initial value solver. It is also used in PDE solution, but it is primarily famous for ODE solution. So here in this lecture, we'll talk about few interesting applications of numerical solution of ordinary differential equation using fourth order Runge-Kutta. We'll talk about a class of models which we call population growth models. Population growth models are models which are given by set of ODEs. It models how the population of an organism will grow in time. This organism could be plant, animal in a forest, or even human, or in epidemiological sense, it could be certain vector which is bearing a disease. Overall, this is an important idea for biologists, and they have worked for last couple hundred years on this model. Of course, this is not a biology class, but the portion that we will talk about that doesn't require biology, it only requires the solver for ordinary differential equations. And you will see that how simple equations can give us rich information about complex phenomena. One of the early model of population growth is what we call the exponential model or exponential growth model. Here, the variable x, a function of t, this is the population of an organism at time t. At time t equals 0, the organism population is x0, which is known, and that is the initial condition for us. The governing equation tells us that at time progresses, the population x will be given by this differential equation dx dt equals ax. Clearly, this is an initial value problem. Here a is a constant which is called the population growth rate. This model is, however, very simple, and we can solve this model very easily. It doesn't require any numerical method or any elegant analytical method as well. I can simply write that dx dt equals ax to dx by x equals a dt, and then I can integrate both sides to have x equals capital A, which is a constant, multiplied by e to the power at. To get the value of a, I have to use this initial condition, and for t equals 0, e to the power at equals 0, which gives us x0 equal a, or the final result from the model is x equals x0 e to the power at. As you can see that this is a very simple model. The main problem of this model is that the population keeps on growing when a is greater than 0, and population keeps on decreasing, coming to 0 when a is less than 0. Population growth never stops, and it will hit infinity as time progresses, which is really unrealistic for any organism. As any organism grows, there will be always resource crunch, and it will either plateau or it will come down, again go up. Many things can happen, but all those complexities are avoided in this model. That is why this is the simplest model, and this is also very old model. Now subsequently, many new models have come which have improved this one. So one such model is something we call Verhulst model or logistic model. Verhulst was a Belgian mathematician, and he was modeling the human population growth in Belgium. In 1845, he gave us a new model where he introduced a term P, which he called the carrying capacity, that is the maximum sustainable population, beyond which Verhulst expected that the population will not grow any further. So the model comes out to be like this. dx dt equals ax 1 minus x by p. This is true as time progresses. At initial time, the population was x naught, as we have seen in the exponential model. So here, compared to exponential model, with ax there is an a by p x squared term. So we can see that when a and p are positive, this will bring a negative term in the equation, means it will bring the population down. Probably it will help the population to plateau. Such equation can be solved analytically, and you have already solved such equation analytically in our discussion in analytical solution of differential equation. These are the class of equation which are known as Euler equation. We can divide both sides by x square so that we get this x minus 2 dx dt plus a x minus 1 minus a by p, and then we can replace this x to the power minus 1 with a new variable. With this change of variable, this will become a linear differential equation which can be solved easily. We have already discussed such equation. You can go back to that lecture if you don't remember how we have solved it. But this analytical solution is important in this case, so try doing the analytical solution. Here, if we go through the analytical solution, we get the result as x equals x naught p a to the power at divided by p minus x naught plus x naught e to the power at. If I divide both top and bottom by e to the power at, the expression turns out to be x naught p divided by p minus x naught e to the power negative at plus x naught. Now you can see that when t grows, when t is very large, assuming that a is positive, this e to the power at goes to 0, which means this entire term will go to 0. Then x will be x naught p by x naught, so it will reach toward p. That's it. As t tends to infinity, limit x equals p for, of course, a greater than 0. Therefore, the model suggests a stability. At some point, the population will stabilize. So now, let us solve a problem using this model. And because we have analytical solution, we will be able to actually match it and see that if we have done it correctly. So let us take this case. Let's say that in a forest where maximum number, that is 10,000 deer, can be sustained, has a current population of deer of 2,000. Now we have to predict the population of deer for next 20 years. This seems like a trivial problem, but these are the problems very important for ecologists. And of course, the ecologists use a lot of complex model. This is a simple model, but this is a very good beginning if you want to learn and go in that direction. Here, a is given to be 1.2, but we can see when we solve it, we can see what will be the effect of a. If we plot the result, we will be able to see. So let's try it and see what happens. Here I have already written the fourth order RK algorithm. Xi plus 1 equals xi plus h by 6 multiplied by k1 plus 2k2 plus 2k3 plus k4. And k1 is f ti xi, k2 is f ti plus h by 2 plus xi plus hk 1 by 2, etc. etc. We are going to solve this logistic model, that is dx dt is equal to ax multiplied by 1 minus x by p. Here the initial condition, that is at time t equals 0, the population is x naught, that is given as 2, that is 2000 deer. Growth rate is 1.2 and it will plateau at 10,000. So P is 10, that is the carrying capacity of the forest. I have written the analytical solution here as well. And at the end, we will match our solution with this analytical solution. So let's start then. At this point, I'll urge you that you can stop the video and get ready with your programming tools, especially if you are working in Python. If you are not working in Python also, please follow the logic and write the program in your own language. For those of you who are not doing any programming at all due to some reason, please keep on writing the pseudocode as I go on writing the program. So here I am in this code window, and I'll start by writing the RK algorithm first, because that is what we need anyway. So in RK, we have to take some of this function, and this function, for this function, I have to calculate this K1, K2, K3, K4. So let us start with this. For I in range n, I have this K1 equals something, K2 equals something, K3 equals something, and K4. So this, as I go in range n, this calculates the variable, in this case this x, from 0 to n, but 0 is the initial condition that we know. So for initially we have this time t, which at time t equals 0, it was 0, and x at time t equals 0 will be given by initial condition x naught. So we have to write somewhere this, that this x naught equals 2. Since this is the initial condition, so in this array the 0 is taken, we have to start from 1. We will go to 1 to n minus 1, and all these are t and x are arrays. So we start putting the constants here. We have this a equals 1.2 and p equals 10, and it's best to write here t naught. So we write t naught equals 0, x naught equals 2, and we'll go up to certain tn, that is where we will stop the calculation. That would be 20 years. So we take is at 20. For these arrays, we have to give a number n. Let us say we have 101 division, which gives us the step size h. That would be this tn minus t naught divided by n. All right. So now we have to make this t and x to be arrays. So to get arrays, we have to import numpy. T equals np zeros. So I am initializing with 0, and this is n, and the same will be for x as well, that is np zeros. So now we need another array that will give us the exact solution. So let us say this is x exact. That will also be this np zeros n. I think this completes the description of all the variables. X exact also we have to give the initial value. We give it as good as this x naught. Okay, all right. So now we are ready to go. Here I have to calculate this function, so it's best to describe this function, and I can define this function as a lambda function. This is lambda function of t and x. These are all functions of t and x. So lambda functions of t and x, and this will be a multiplied by x multiplied by 1 minus x by p. P we have described already, so there is no problem. So K1 is the value of this function at some points, some x and t, and all of them are values of this function. Okay, and then once we calculate the values of this function, then my x I will be equal to x I minus 1 plus this h multiplied by this k1 plus 2k2 plus 2k3 plus k4 divided by 6. I have to also find out the exact. So x exact I will be equal to this one, x naught p e to the power at divided by p minus x naught plus x naught e to the power at. Therefore, we can take it as, sorry, I made a spelling error here. Okay, so e to the power at I have to calculate twice. So let's calculate the e to the power at as r, and then we can write it as x naught p to the power at x naught p r divided by p minus x naught plus x naught into r. So here I have to figure out the exponential. For that I need math. So this is math dot exponential of a t I, but t then I have to update. So ti is equal to ti minus 1 plus h. All right, so we are done. Now all we have to do is that we have to properly write this k1, k2, k3, k4, and this is where we make mistakes. So here it goes from I to I plus 1, but you have to understand here we are going from I minus 1 to I. So this ti xi, etc. will be ti minus 1 and xi minus 1. So ti minus 1 and xi minus 1. Okay, so I have copied it everywhere. Now for k1 I am all right. K2, this has to be added by h by 2, k3 h by 2 and k4 h. So here with t I will add here h by 2, here also h by 2, and here h, and on the other side here h k1 by 2, h k2 by 2, h k3. So here h k1 by 2, here h k2 by 2, and here h k3. Okay, so we are all set, but now we have to see that if we are doing, okay, here I made a mistake. Okay, so we have to plot the result, otherwise we will not see what we are getting. Okay, so let's come out of this for, and to plot it, of course, I have to bring this matplotlib. Okay, matplotlib pyplot as plt. Okay, now we'll plot the results. So plt plot t and x. Okay, let us see that how it comes, and then we'll plot the rest of the things. Okay, so hopefully this is good. So let's try it. Okay, you can see that it is giving something. It is also giving, yes, so it is giving something. We have to now see that if we are getting the right thing. Okay, so this is x, so we can plot exact also. Okay, so here at x-axis I have time and y-axis I have the population. So PLT x label time in year and PLT y label will be population in 1000. Now this plot we can give some color, black, and here I have color that is blue, and let's see it. Okay, it's all blue, black is not showing. That means black is just behind it. So we have to segregate in some way. So we give it give my black a symbol and give the blue line. So let's plot it once again. Okay, so this is okay. And put the comma here. Here also and then put comma. Okay, now we can see that one over other is coming, and because it is line, it is connecting over this black dots and line we can see now. So maybe we can remove some of these black dots, and okay, so now it's much clear now. You can see that this is my population and this is the year. Let me put the grid here. Okay, so now with grid you can see that it is hitting the maximum, that is 10,000. That is what we were hoping for, and because our P is equal to 10 and the maximum is 10,000, it is hitting 10,000 in like 7-8 years, about in 10 years you can say, and after that it has plateaued. Very quickly it has grown. We actually need more points here, it looks like, but anyway this is only for our learning. So the steep rise is because of this high growth rate 1.2. If we for instance have a growth rate of let us say 0.5, then this kind of growth will probably not happen. Let's see, you can see that now the growth is far more gradual. Okay, if I have growth rate let us say 0.3, you can see that it is gradual. It has not hit the plateau yet after 20 years. Okay, so this tells us the efficacy of this is a very simple yet very elegant, beautiful model. It gives us the big picture of how the population will grow. Okay, all right, so let's see that how we can actually improve this model. So you remember this was the problem that we were solving, and we have solved the problem. Now you see that both the models, they have certain major limitations. The limitation in this case that they do not consider the tiger population that could be in the forest. So tiger can actually kill some of this deer, and that would be one of the reasons that deer population will come down. If there are more deers, the more tigers will survive and they will kill more deer. On the other hand, if they kill more, then the tigers will not survive because they will not have enough food. We are assuming a very simple model here, that tiger eats deer, and if there is not enough deer, tigers will die. So it tells us that more tiger means less deer, and less deer means again less tiger. Less tiger means more deer. So again, more deer means more tigers. So this is how the model will go. This is a very funny model. So how we can bring this idea into picture? So let us see that what other models we can have. One of this model is that something we call Lotka-Volterra, that is predator-prey model. Predator-prey model is actually an improvement over the exponential model, as much as it is this. Our previous model, logistic model, was an improvement over the exponential model. Here the Lotka-Volterra model is also an improvement over the exponential model. In exponential model, you have dx dt equals ax. Here, in predator-prey model, this x is the population of prey, or in this case deer, and this y is the population of predator, or in this case tiger. So here this A and C, they gives the rate of the individual population, but then we have this B and R, they give us the idea that what one population will do to other. This is the B and R, actually the interaction parameter between predator and prey. This A, B, C and this R, we take them as constant. So with this model, it's very difficult to actually simulate this analytically, but what we can do is that we can remove this t time, because t does not appear on the right hand side. This gives us certain idea that we can remove t and we can write it as dy dx equals this minus cy plus rxy divided by ax minus bxy. So this gives us some idea. We can solve this. When we solve this, of course, we don't get the time variation, but we can get the idea that how the solution could be. So what you can do, that we can now separate this x and y. So I have y by x here, and if I take the y out, it becomes minus c plus rx, here a minus by. So y and x are somewhat separated here. You can see that this is by minus a by y and rx minus c by x dx. So this is now, we can break it down, b dy, a dy, y, r dx, c dx dx. So we can integrate all these terms and we can get a result like this. by minus a ln y plus rx c ln x will be equal to certain constant whose value will come from the initial condition. Here the initial condition was x equal to time t equal to 0, x equal to x naught, and time t equals 0, y was y naught. So here time doesn't appear in this equation, but we can write that when x is x naught, at that point y is y naught. So that gives us an initial condition here, and then we can evaluate k. But then it doesn't give us much, because this equation is such that it's very difficult to understand what will happen to this population of each of these x and y. But what we can do is that actually we can plot this. This is an implicit function, but it can be plotted using software, or you can take certain value of x, calculate y. That calculation will be very difficult. That is why it is better to use some software to directly plot it. I'm not plotting it here, but this is just, I'm showing you that if I plot it, it will actually look something like this. So it will look like sort of this circular or elliptical type figure, this different size of pen. Okay, so again we'll see that how we can write the computer program for this problem, and what kind of result it can give us. So here I have written the predator-prey model, that is dx dt is ax minus bxy and dy dt minus cx plus rxy. Sorry, it would be cy plus rxy. Okay, and this values of ABCD is somewhat arbitrary. A was 1.2 you are taking, so I have taken 1.2, and BCD I have taken from your textbook. There is an example there. From there I have taken this BCD. They are reasonable values. So now let us see what we can do. So we'll take this program and we'll improve over it. So this is a copy of the previous program, and so here I have new constants. So a equals 1.2, then I do not have a p here. I have b equals 0.6, c equals 0.8 and r equals 0.3. t naught is 0 and x naught is 2. I have to take an initial value of y naught, and I am taking that as 1. So this is our predator population initially. I have taken that as 1. Tn I am taking as like 30. because I'm taking it 30, I'm taking n slightly large. We'll go look into 30 years now. All right. So because this is the number of points I am taking, my t minus h will be this minus n minus 1. I was taking n previously, but that gives some error there. This should be n minus 1. And then I have t here, x here. I do not have an x exact. All I have is an y. Okay. So now this k's, I have now different k. One set of k for x and one set of k for y. So I have this, because I have different k, I have different x, different f also. So I give one f for x and another f for y. And this should be function of both x and y. So this is a into x minus b into x into y. And here I have minus c into y plus r into x into y. In the initial condition, I have to take the initial condition of y, and that is my y naught. T naught is 0, x naught is 2, y naught is 1, tn is 30, n is 301. We are all set, but then I have this, as much as my x is being updated, I have to update the y as well. So let us first see the update of x. So this will be my then fx, and along with x there will be an y as well, because in the function y will also come. So I take this. So all these k's are for x, so I name them as kx. X is updated like this. So here these are kx. So I need something for y. So as much as I am calculating kx's, I have to calculate ky as well. So this would be my ky1 and this f of y. Similarly here ky2, this should be f of y. kx3, similarly I have ky3 and kx4, ky4. So now just like x, here I have y, and these are all y, but y I have to write it properly, because this is increment here is h plus kx1. With y the increment will be h plus ky1. Here the increment is kx1 by 2 in and this ky1 by 2 will come as the increment. Then in calculation of 3, this should be ky2 by 2, and in the same way here it should be ky2 by 2. This is hkx3. That means here I'll have hky3. So this is my, this actually completes it. But now I have to find out I have to plot it. Okay, so I'll just put this plot as plot tx and plot. Okay, and we have to give a legend here. So I have given this prey and predator as legend, because x is the prey and y is the predator. So let's see what it gives. Okay, so we have corrected the legend, but we made a mistake here. This is not the correct plot. So let's see what we did here. Problem will come from here. So here this has to be fy. This has to be fy. So let's try once again. No, this is not right. Okay, so now we can have the desired result. You can see that I made a mistake here in fx and fy. That is why it was giving so much problem. So now you can see that the way the process will go, the prey population will increase. Initially the predator will decrease, but then it will go up as well. And then because of this increasing prey population, the predator population is also decreasing. So this cycle goes on and goes on. Predator increasing, because of that prey decreasing, again predator increasing, prey decreasing. This cycle goes on and goes on. So this is a very important model in biology. As I said, it can be improved further, but this is a good beginning. Okay, so we have now seen that two very interesting ODE models we have solved, and we have seen that simple ODE models can give us very meaningful results of practical importance. Both the models are important in biological and ecological problem, and they are of general interest in different branches of science and engineering. These models can be improved in different ways. One way is that we can use our logistic regression model that we were working on previously, and that was this model. And in this model, we can add then the predator part. Predator model will remain same as predator-prey model. Then we can simulate this model and see what happens. I'll urge you that you go on and run this model. My guess is that what you will see that because of this P here, both the population will stabilize, but they will undulate for some time and probably they will stabilize. This of course depends on the value of P and ABCD, how it will behave. So that's all for this lecture. Thank you, and I'll see you in next class.